Hello again guys, Neeraj here from IIT Roorkee EPH. In this video, I'll be explaining you guys the LVDT experiment that I performed. So what is LVDT? LVDT stands for Linear Variable Differential Transformer. Breaking down the acronym, linear means the linear relationship between the input and the output produced by this device. Variable is the variable input that we are going to give to this device using an AC source, and differential is the difference between two inputs that we are going to calculate and measure. And lastly, transformer is a device that transfers electrical energy from one circuit to the other using inductively coupled conductors. So you might ask the difference between transformer and transducer. So transformer is limited to AC current only, whereas transducer is a more general term. So transducer is a device that changes one form of energy to the other. Let's move to the principle behind the experiment. So this experiment is based on the concept of mutual inductance. The LVDT setup is made up of three coils and a core. So primary coils, two secondary coils, and a core which is made up of different materials such as soft iron, hard iron, copper, etc. and will help us to measure the displacement. So when we pass an AC current through the primary coil, it produces mutual inductance in the secondary coil, which will be given by the formula in the second line. M equal to N phi by I, where M is mutual inductance, N is the number of turns in the primary coil, I is the current in the primary coil, and phi is the flux produced in the secondary coil. And the EMF generated in the secondary coil due to this mutual inductance is M di by dt. Also, there will be an opposing flux due to Lenz's law in the secondary coils. Now, this whole experiment and concept will help us to measure the displacement of any core or any sample in this setup. This is a schematic diagram of LVDT. On the left is a core at the null position, and on the right, we can see a displaced core. So speaking of the left diagram, when we pass a current through the primary coil, it produces mutual inductance in the secondary coils. Also, as the core is at null position, the changes produced in both the coils, secondary coils, will be the same and there will be no difference in the output. This is the ideal case. When the core is at null position, we get a residual voltage of which I'll spec in the next slide. On the right, we can see a displaced core. So when we move the core in or out of the setup, the core comes in front of any one of the coils, thus changing the flux in the particular coil and hence the mutual inductance and hence the EMF. So we get a difference in EMF between the coils which can be measured using different signal conditioning units. So the factors to consider while performing this experiment is the linearity. Whenever we talk about transducer or sensors, linearity is one of the important factors that we should consider, and linearity should be maintained in both of these devices. So speaking of LVDT, the linearity between the input and the output is for a limited range because after a certain range, the non-linearity factor in the calculations becomes dominant. Also, as I said, at the null position or zero position of the core, we get residual voltage due to the magnetic and electrical asymmetries. Here is the formula that was of which I was talking in the previous slide. So on the left side, you can see the formula. You can see after a certain range, where L becomes dominant, the non-linearity factors will become considerable. And the B figure shows us the linearity range. So let's see the practical video that I have performed. So this is the LVDT setup, which will help us to move the core in or out of the secondary coil using a thumb wheel. So this is the scale and you might see a white line which will help us to measure the displacement of the core. Showing the digital voltmeter where we'll see the demodulated output using the wires and the connections. This is a CRO which will help us to measure the modulated output. Now, I didn't talk about demodulated and modulated output. So let's see what is demodulated and modulated output. So modulated output will help us to measure the linearity range of the LVDT. So as modulated output is the VRMS, that is root mean square, we won't get to know about the displacement of the core, whether it is positive or negative. Here comes demodulated output. Now what we do is we multiply the modulated output with a carrier signal having frequency same as that of the input signal. And after performing some calculations and passing the modulated signal through low pass filter, we get a linear relationship between the demodulated output and the displacement, thus helping us to measure the displacement of the core, that it is moving on the left or to the right, that is in the positive direction or in the negative direction. Yeah. So here I move the thumb wheel to change the position of the core. As you can see, I'm moving the thumb wheel to make the core displace to the negative side. I moved it to -1 centimeters. Corresponding to the -1 centimeter, this is the demodulated output, and this is the modulated output, uh, the RMS voltage that we are going to measure. So this is the output of the experiment. On the left side, you can see the modulated output. On the right hand side, you can see the demodulated output. So as I said, the modulated output will help us to know the null point, that is what is the residual voltage, and the linearity range, like in what range we'll see the linearity between the input and the output. And on the right hand side, there is a demodulated output graph, which will help us to know whether the core is moving on the left hand side or on the right hand side, that is to the positive direction or to the negative direction. Now coming to the applications, LVDT finds wide applications in real life, such as industrial applications, aerospace, defense, medical applications, etc. This is a device that will help us to measure the displacement of any material or any sample. So in industries, for precise motion sensing, in aerospace, for monitoring the movement of different components, etc. In or in medical field, for in MRIs, we can use LVDT to know the displacement. Yeah, so this is all about the experiment that I have performed. Thank you.